So in today's lecture, we will see the flexible solution for flexible electronics. Flexible solution for flexible electronics, right? So I'm Dr. Surya Sharma, who's the faculty in the Institute of Aeronautical Engineering. Okay, so today's lecture we'll see the flexible solution for flexible electronics. Okay, so the contents, the introduction. So introduction, objective. In that we will see what is an objective, and fabrication of thin film transistors, that is TFT, and other is a competing technologies, and other is the solutions. So if you come to the introduction factor, thin film transistors are highly interesting topic of research. Applications are flexible and large displays, radio frequency, heat tags, and variable electronics, chemical sensors. So these are some of the applications of this particular technology, that is flexible electronics. So the thin film transistors are highly interesting topic of research. We have flexible and large scale, large displays, radio frequency, heat tag, variable electronics, and chemical sensors. So what are the challenges? The challenges are mechanical flexibility, and we have the durability, we have the lightweight, and good registration over large area, and we have the good performance of the device, and low cost and high throughput, right? So these are the challenges what we obtain. So the main objective of this particular flexible electronics is a small study on the material properties, and a study on the available technologies, pointing out a possible combination to fabricate transistors of desirable performance. So these are the main objectives of using the flexible electronics. So when can we display something? So when can we display something, and what we need to display? And this what we need to display is controlled by TFT. TFT means that is transistor foundry technology. So why you see in the TFT? TFT is nothing but thin film transistors. So what to display is which is controlled by thin film transistors. TFT means thin film transistor. Thin film transistors. Where to display? The way to display is on a flexible plastic substrate, and how to display is on pixels. So the pixels is made by LCD, that is liquid crystal displays, object OLEDs, and E-ink. So these are some of the display technologies where the thin film transistors are being used, right? So that is a flexible plastic substrate, and how to display, that is pixels, LCD, OLED, and E-link. So this is what the active matrix of liquid crystal display with the thin film technology. We have some color filters. We have the substrates, that is plastics, and we have the transparent electrodes. And we have the display black paint, and we have the substrate plastic, and we have the pixel with 3FT driver columns and row drivers, right? So these are the active matrix liquid crystal display with thin film technologies. So the fabrication of thin film technology on plastic substrate is inorganic thin film transistors, that is ITFT, and organic thin film transistor, that is OTFT, right? So ITFT and OTFT are the two fabrication technologies of thin film transistors on plastic substrate. So what is this ITFT? ITFT is nothing but inorganic thin film transistor. Inorganic thin film transistors offers high switchable speeds and miniaturization, and the problems are cannot be mass produced, they're highly expensive, not well suitable for plastic substrates, right? So these are the problems, that are the gaps that were being framed with ITFT, that means inorganic thin film transistors. So in organic thin film transistors, solution processed organic semiconductors, solution processed dielectrics, inkjet printable conductors, low temperature processing, low cost printing techniques, and performance is limited mainly because of mobility of the semiconductor, right? So solution processed organic semiconductors, solution processed dielectrics, inkjet printable conductors, low temperature processing, low cost printing techniques, and performance is limited mainly because of mobility of the organic semiconductors. And we have the transistors, we have the organic semiconductors, we have the gate, source, drain, we have the gate insulator, substrate, that is PET, PES, and we have Here we have the semiconductor, we have the substrate, we have the gate, insulators, and we have drain and source, and between a semiconductor is being sandwiched, right? Whereas in case of this here, here we have the source, we have the drain, and this is insulator, this is gate, and this is substrate. On this substrate, these all materials are being fabricated. So that is what the transistor, organic semiconductor, gate, source, drain, gate, insulator, and substrate, that is PET and PES. So in case of organic semiconductor, pentacene is the best one. So which we have the mobility centimeter square per volt second, and we can see we can see on the silicon wafer. This is on silicon wafer, polysilicon, and this one, and this is the capability of it. This pentacene is the best one that we can see, and we have the gate, source, drain, and dielectrics, gate, source, and drain characteristics, right? So AU is the most widely used electrode for gate, source, and drain. So GaN insulators are all depolymers, right? So PMMA, PVP, PVA, and polymer. So whose mobility work function is being shown for different materials like aluminum, zinc, silver, vanadium, and platinum, and all materials have been shown the mobility and the work function of these particular materials, right? So what are the compounding technologies? Microcount printing, it is a soft lithographic technique uses lithographic technique uses an elastometric PDMS stamp to form patterns of self-assembled monolayers on the substrate by contact. It has potential to pattern large areas quickly, whose resolution is around 30 nanometers. And this is what the stamp PDMS inking, ink solution printing substrate and flat surfaces. We have the directions of motion silicon or say SiO2 glasses, PDMS, SiO2 glass, and corroded glasses, and all. So these are what some of the surfaces what we have. Okay. So Rogers et al. Have prepared transistors on plastic substrate using micro CP. They have prepared organic active matrix black pane of the 256 transistors on 5x5 inch, whose resolution is 10 to 50 micrometers. On-off ratio is 1000, and substrate is PET, and gate is ITO, and the semiconductor is pentacene, and the source or drain is AU. And this is what we can see here. This is what the 12 centimeter, right? So 12 centimeter, the organic active matrix backplane of the 256 transistors on 5x5 inch transistors or 5x5 inch silicon wafers or any other substrate. So nano transfer printing, it is a combination of photolithography and transfer printing. Nano transfer printing, it is a combination of photolithography and transfer printing. And flexible substrate is not exposed to any lithographic technique. Patterns are created on silicon, transfer substrate by photolithography, then transfer to plastic substrate by imprinting. Then transfer to plastic substrate by imprinting. Patterns are created on silicon, transfer substrate by photolithography. So this is the schematic of the process: the transfer substrate 1 and device substrate, transfer substrate 2 and transfer substrate 3, and these are the schematic of the process. So substrate is PET, semiconductor pentacene, field effect mobility is 0.01 square centimeter per volt second, on-off ratio is 10 power 4, gate, source, drain electrodes are gold, gate insulators are PMMA, that's a polymer. So thermal transfer printing, it is a dry transfer printing technique. It is a large scale printing patterning technique that gives us high resolution, good registration, and high speed processing. A donor substrate is coated with the material that is to be patterned on main substrate, and features are selectively transferred by laser beam exposure, right? So it is a dry transfer to printing technique. It is a large scale patterning technique that gives high resolution, good registration, and high speed processing. A donor substrate is coated with the material that is to be patterned on main substrate, and features are selectively transferred by laser beam exposure. So this is the schematic of the process. We have source, drain, gate, interconnects were printed with DNSSA or PANI or single wall nanotubes, and the process is highly flexible and resolution is less than 50 micrometer. It is a dry transfer and purely additive. So micromodeling in capillary. We place the PDMS mold on a support and PDMS mold. Okay, that is a polymer. It is a soft lithographic technique. It makes use of PDMS stamp and capillary action to prepare the pattern, and resolution is 350 nanometers. And place a drop of a polymer solution at one end, fill channels by capillary action, evaporate solvent, and remove PDMS mold. And organic semiconductor is polythiophene, whose feature size is 25 micrometers, and substrate is PES. gate, source, drain, and pani. This is also one of the electrode, right? So mobility is 0.001 centimeter square per volt second. Micro transfer molding. It is a soft lithography technique. Make use of PDMS stamp to transfer the pattern. Pre-polymer is applied to PDMS stamp and put on the substrate and cured to leave the pattern. High resolution is possible, and we have the pre-polymer PDMS and remove excess pre-polymer PDMS placed on the support, cure, remove mold and residual film. This is what the residual film is. Another flexography printing. Flexography is a mechanical printing method used for the mass production of printed matter such as newspapers, cartoons, packaging, and plastic films of material and plastic filling material, right? Plastic material. So the process overview steps involved are image preparation, plate making, printing, finishing, and these are the steps involved in process overview of it. And the step involve an image interpretation, image preparation, art supplied by the customer. So plate making. Plates are made of flexible materials such as plastic, rubber, or UV sensitive polymer, photopolymer, so that it can be attached to a roller or cylinder for ink application. We have photomechanical, photochemical, and laser engraved plates, direct digital plate making. So we have the printing. This is what the analog rolls, and we have the plate cylinders and the impression cylinder. Finishing may include operators such as coating, cutting, folding, and binding. And the problem is, if solid content of the ink increases, then a surface roughness increases and good adhesion is difficult to achieve. And transistor characteristics are inferior, right? So this is a table shows the viscosity and conductivity of the flexo printed lines as well as the estimation of the surface roughness. So we have the solid content around 6.28%, viscosity is 25 degrees centigrade, and line thickness is 450 nanometers, and conductivity is 8.5 s per and the surface roughness is good, and these are the transistor characteristics which are inferior. So if you see the integrated process, we have the top writing printed on the particular reel-to-reel process steps of polymer transistor. So we have the gate conductor pin, we have the gate dielectric bladed, semiconductor polymer bladed, copper wet etched, and we have the substrate, and multi-layer dielectric printed, top writing printed. So these are the proceedings which were taken from the IEEE in August 2005. So these are the schematics of reel-to-reel processing steps of polymer transistor. So PET foil, PET foil with copper cover layer, patterning by UV lithography, SIPOSA to reel-to-reel exposure and alignment system. Afterwards, the resist is developed in an alkali solution into an R2R development unit. Etching, copper is etched in Na2S2O8 solution, and finally the resist is stripped in 3 kilobit of potassium hydroxide solution as R2R reagents. And this is what we can see the film. The first copper metal lithography in reel-to-reel process, and the second one is single separated test chip, and third one is lithographic drain source with L equals to 10 micrometers. Right. So this is what the process technology that we use for the fabrication of flexible electronics. So if you see for the inkjet printing, in inkjet printer patterns material by expelling tiny droplets of liquid ink from an orifice one end at a time as it is moved in 2 dimensions approximately 1 millimeter above a substrate. Complete fabrication can be done. Source, drain, gate, electrodes, interconnections can be fabricated, used to deposit various active layers. So what we need to start fabrication is a printer, a flexible substrate, ink. It can be aqueous or solvent medium consisting of desired material to be deposited. So this is what the gate electrode is printed using a gold nanocrystals, and a source or drain contacts are printed using gold nanocrystals. And these were on a substrate. We have the polymer dielectric is deposited via inkjet, and we have various active layers are deposited via inkjet. And this is a variation what we can see. From the proceedings that have been taken in 2005. And what are the drawbacks of this technology? Difficult to produce transistors with channel length less than 10 micrometer. This technique has not been applied to organic transistor because its resolution is limited to 20 to 50 micrometer because of the spreading on the substrate. Right? It is difficult to produce transistors with channel length less than 20 micrometer. So this technique has not been applied to organic transistor because its solution is limited to 20 to 50 micrometer because of their spreading on the substrate. So solution is confining the spreading of the ink droplets on a hydrophilic substrate with a pattern of narrow repelling hydrophobic surface regions that define the critical device dimensions. And photolithography and organic plasma, O2 plasma etching of 500 angstrom polyimide films, right? So photolithography and oxide plasma etching of 500 angstrom polyimide films being. So this is what we can see, the schematic diagram of high resolution inkjet printing, and we have seen the AFM. We can see the AFM image over there, and the schematic diagram of the top gate. Lithography field free self-aligned inkjet printing with sub 100 nanometer resolution. The principle is surface forces exerted on small liquid droplets on heterogeneous surface can be used for assembly of functional nanostructure. The surface forces exerted on a small liquid droplets on heterogeneous surface can be used for assembly of functional nanostructures. So steps involved are inkjet printing of the first conductive pattern onto the substrate, selectively modifying the first conductive pattern to be of low surface energy, subjecting to CF4 plasma, surfactant, and benzoyl chloride. Inkjet printing is of the second conductive layer that partially overlaps the first layer. So the droplet of the second pattern is repelled by a flow of the low energy surface of the first pattern, and the result is sub 100 nanometer resolution can be obtained. And the advantages: less wastage of material. It is data driven. No mask is required, reducing turnaround time compared to lithography. Range of materials can be used. The solution is mainly competing technologies are micro contact printing, inkjet printing, reel to reel printing. Our choice is to go for the inkjet printing, whose feature size is less than micrometer, and reel to reel printing for greater than 10 micrometer. So the materials which use are electrodes, AU or AJ or PANI, or dielectric materials like polymers, right? And semiconductor polythiopenes displays and pentacene RFIDs, and preferably top contact gate use of SAM on the surface of the dielectric material. These are some of the materials what we can need to understand regarding the process involved.
Like, share and subscribe. Hit the bell icon for more updates.